Hi, this is my project for numerical computation. So it's about complex numbers. So in this project, I just basically attempt to write a library for working with complex numbers. So the usage of this class is, for example, complex, real, imaginary. So that would correspond to, so for example, 1, 3, complex 1, 3 corresponds to 1 plus 3i. So let's take a look at the class. We have the real part, imaginary part. The modulus function returns the modulus. The argument function returns the argument, the principal argument between negative pi and pi, excluding negative pi and including pi. Argument convention returns the argument, but to fit our preferred convention, I think of between 0 and 2 pi. Then we have a show function. Normal show function prints out the complex number in rectangular form, and final two in polar form and in exponential form. So let's take a look at the quick example. Z equals 1 plus I, so complex 1, 1. So there's their representations. So let's take a look at the modulus. It should be square root of 2. And finally the argument, which should be pi over 4. So 0.785 pi over 4. So next let's move on to the operations. So these are basically simple normal operations that you would expect when working with complex numbers, and these are all functions of its own because obviously we need to find a way to combine objects of the complex class. So we have add, subtract, multiply, divide. We have e to the z. We have log z. Know that this is the principal argument, the principal branch of the logarithm. We have two power functions. This first normal power is computes a complex number to another complex number, while int power is suitable for z to the n, where n is an integer and z is a complex number. Next, we have the nth roots of a complex number. So as a quick example, let's say I want to find the sixth roots of the number 1, or the sixth roots of unity. So the function nth root returns a list of complex numbers, and I'm just going to show them all out here in rectangular form. So there we have all of them. And finally, we have sine and cosine functions, which are written by their definition within the complex numbers. And basically from these two functions, you can derive every single known trigonometric function. So that's nice. Next, we have the section of visualizing complex functions. So basically this image function that we have right here takes a region of the complex plane, commonly denoted by omega, and pumps it through the function f and plots the image. So we also have this normal plot function, which just plots any given region. So a list of complex numbers, just plot them all out into the 2D plane. Then we have three types of regions. We have rectangle, we have a disk, and we have a ring. So as an example, let's say I want a disk of radius 1 centered at the origin, and let's make it a semi-disk, so data runs from 0 to pi. And let's plot this. Next, for example, let's plot a ring with inner radius 2, outer radius, inner radius 1, outer radius 2, centered at, let's do 1 plus I, and let's make it a full ring. So here we have it. Now let's actually look at what this function omega does, the image function. So I have some example functions here. have f of z, which is z times 1 over root 2 plus I over root 2. So it's a simple linear function. So now I'm going to take this region, this rectangular region R, and plug it into f and see what it gives me. So here on the left we can see the input region, and on the right the output region. So if you notice, this input region is being kind of rotated 45 degrees counterclockwise. So that should make sense because the argument of 1 by root 2 plus I by root 2 is pi over 4. And now let's take a look at another example. Let's say this function g is defined by z times the sine of z. And we're going to take a semi-disk. Yes, a semi-disk, the upper half of a disk, to be precise, of radius 2 centered at the origin, and we'll throw that into G and see what we get. So we get something that we can call, I think this is called the centroid. So yeah, this is how the image function works, and I think this is particularly useful because, you know, we can kind of visualize how certain functions can act like transformations at times on certain regions of the complex plane. And, you know, it gives us a way to quickly plot functions, the inputs and the outputs, and see how they correlate. And we can see some interesting results. Next section is the complex derivatives. So we have this function diff, which computes f prime of z. And now that we have that, oh, and by the way, this h is just the parameters having to do with the difference quotient. So now that we have the f prime of z, we can do Newton, which is given by the same formula as in real variables. And we also have some, you know, helper functions. Polynomial is to create a polynomial of degree n with coefficients in descending power. And we have sum functions, so summing together many functions, so we don't have to do nested adding. So let's do a quick example of Newton. So I have this polynomial here, p, which is a polynomial of degree 5, and the coefficients are as shown. For example, so 1 plus I z to the 5th power plus z to the 4th minus 1 plus I to the 3rd power, and so on and so forth. So there we have a root of complex number of this polynomial p, but a limitation is that it doesn't guarantee to find every single root. Even with, you know, finite amount of searching, you probably can't find or are not guaranteed to find every single root of an nth degree polynomial. So, but at least it gives us a root, and it will converge to a root given enough iterations. And finally, we have this zeta function. So this is kind of, you know, pretty common thing to mention when working with complex numbers. So let's compute zeta of 2. So if you can remember, zeta of 2 is the reciprocal of the natural number squared, and it converges to a special constant pi squared over 6. And I'm going to run that 500. So the 500th partial sum of this zeta function, because obviously we can't compute to infinity. So pretty close. So yeah, this is basically it for this project. I tried to implement a way of finding all the roots of a polynomial, but that is, I think, a little bit too complicated because it requires putting it into matrix, finding the eigenvalues, and yeah, it would be computationally expensive. So yeah, but I think this is sort of good enough in my opinion. So yeah, that's it. Thank you.